So yeah, it's me again, Bernard, and I will talk about how to prepare climate projections to account for potential offsets between your historical data and the uncertainty to incorporate this into MSE simulations. And maybe you have hoped to already fit some models or run some MSE simulations. I'm sorry, it's all about data preparation again. So yeah, bear with me. So here's again an overview graph from the WK Eco MSE report. This time it's a bit different, although it looks quite the same as the previous one. And okay, we are now that we have our environmental covariates selected for the historical part, and we also got our hands on some nice downscale climate projections. And we are here now, so yeah, all the other parts will come the next days. And what to do now, right? So what type of data you might have. So for your historical data, you have picked your observational data or reanalysis data set that captures the internal signal very well. You have a very good data set that spans a large historical period, maybe from the 60s up until now. And this data set also has an equivalent in the respective future projection. And for the North Sea, this would be for example, when using the temperature data from the Ahoy dataset and also the salinity data from the Ahoy dataset, and currents data from ORAS-5, which is also a reanalysis. And for the climate projection for the future, we would use the Polkom's Asm dataset, which is a regionally downscaled ocean model for the climate projections RCP 4.5 and RCP 8.5. And yeah, they have a different extent, and their overlapping period is from 2004 to 2020 approximately. And how do we link those two data sets? Well, for the Polkom's Asm, we don't have a continuous data product, right? As I recall, it's only from 2004 to 2099, but you might have a continuous data product from 1980s to 2099. Then you can just continue, but be aware that for the historical period, the internal pattern might not be perfectly resolved. This is the case for the Nemo Medusa dataset, for example. And in our case, we have different data products for the history and for the future. And when we just plot those data against each other, we see that there is a bias, right? So this is raw temperature. I think it's the mean temperature over the North Sea. And the black line would be the historical period, and the red and green lines would be the RCP projections. And you see that there's quite a big difference, and they don't overlap. So you need to correct for the offset of the different data, and you might do this via bias correction. And what can we do? Well, there are different methods out there. One is the delta method, also called mean bias correction, where we just remove the mean bias between the historical and the future data for each grid point in the case of spatial temporal data, and we calculate an offset in the overlapping period, for example, and just remove it. Or there's a different method called quantile mapping, where you try to also correct for the mean bias, but also try to correct for variance differences, right? When your projection has a different variance than your historical record. And there you try to match the empirical distribution function of the data and map the quantiles of the projection to the historical part, which allows to correct for the difference in variance. And I made a tutorial already a year ago, which can be found on my Figshare account, which goes through all the different steps to do this. And we also want to look at this tutorial in particular today. Just quick words on the mean bias correction. This is a rather simple way to correct for the difference in mean between two time series or spatial grids. And the steps are quite easy. You decide on a time period for which to remove the mean bias, the offset, This could be the mutual overlapping period, and then you calculate the mean for the historical time series in this overlapping period and the projected time series, the mean. And you calculate the bias, and then you remove the bias from the projection. For quantile mapping, it's a bit different. The quantile mapping method directly on the raw data is not really trend preserving, so therefore you need to do several pre-processing steps to get a meaningful trend. So for a case here where you have simulated data in a historical time series which a low variance and a specific trend, and a projected time series with a high variance and a different trend, and you want to match the projection to the historical variance and the mean. And you first decide on the time period to base the quantile mapping on. There you can use again the overlapping period, and you remove the individual trends from both the historical part and the projection in this correction time period. There you have it. You determine both time series in this period, and then you fit your quantile mapping model to this trend corrected data. Then you remove the trend from the whole projection period, here in orange, and apply this fitted quantile mapping method to this trend corrected data for the whole projection period. And then you calculate the mean bias, of course, same as the delta correction method, and add everything back together. So the quantile map projection minus the mean bias plus the trend will get you the orange time series in the last plot. And you see quite nicely that the variance is quite well matched now to the historical record, and also the trend is preserved. And what to do now with uncertainty in future environmental data? For your MSE simulations, you might run them in a Monte Carlo fashion, and you have only one time series of your climate model available. So what to do now? So there can be different versions. Okay, you have various different climate models available. So this would be the first case. You have, for example, Polkom's Erdem for the North Sea, Nemo Medusa I already talked about, and there's also another one, MPIOM, Max Planck Institute Ocean Model. And those different climate models and ocean models have a different variability, uncertainty attached to them, and their model runs and the spread between the model runs looks quite different, right? And this would be the preferred option if you get your hands on various climate models and climate model output, to use those in your MSE simulations. But what if you only have one climate model, for example, the Polkom's Erdem model? Then you can only model the within model variability uncertainty. And this is the case I want to talk about. So sometimes you have only this one future climate model available and only one particular realization, one time series, for example, of temperature. And in a stochastic MSE simulations, you want to run more than one run with variability coming from stochasticity. So how to generate several realizations of your process for the future that preserves the trend and the autocorrelation of the data. And the idea is now to create those realizations artificially, but bound to the original data, so that they capture the variability and the autocorrelation of the original time series, but also the relationship between different variables, because you might have take into account temperature and salinity in your MSE simulation, and you want to preserve when the temperature, for example, goes up and your salinity follows the temperature in a specific way in the climate model projection. You want to preserve this. So you want to take into account also the cross correlation between different data sets. And what I came up with is to use a vector autoregressive model or a Bayesian vector autoregressive model to create those new time series that preserve the trend, the autocorrelation, and the cross-correlation of the original data. You can understand a vector autoregressive process basically as a multivariate version of an autoregressive process, and it models the variable's own lags or past influences to inform the future, but also takes into account other past influences of other variables. And the Bayesian estimation here allows for constraining the coefficients and having a more stable fitting procedure so that the model is more bound to theory, right, by defining priors. And I also made a tutorial for this one. When we have time, we go through it later on. And what I did here to do it for spatial temporal fields is first to do a PCA. We talked about it earlier in my talk. So putting in like the raw data fields, like the SST, the currents, and salinity would be overkill, because you might have like 3,000 or 5,000 grid points and a very, very large model to fit. But when you just reduce your SST, for example, to the first 4 PCs, and your currents, which is a bit more complex, to the first 10, and your salinity to the first 3, then you have only 19 variables that you can put into the BEVA procedure. So you decompose your environmental data, detrend it with monotone trends, and then calculate your vector autoregressive model on this dimension reduced data, add back the trend, and add back also the remaining noisy PCs that we didn't use in the process, and then you can generate new environmental fields in this procedure. So you might say, okay, I want to produce 100 new environmental fields that have this approximately the same statistical properties as the original fields, and then you can do this with this procedure. And here are some examples. So this is like the salinity signal for the summer, for the projection periods from 2006 to 2100, and the original in black, and the red one is a simulated one, so the trend is preserved, and also the large scale oscillations. And when you look at the autocorrelation function, the ACF, you see that they have quite the same form. So the simulated ACF has a bit higher peaks for higher lag influences, but it's more or less the same. So this is quite good. And when you look at the cross-correlation function, for example, when you compare the salinity PC2 with the temperature PC1, then you see they influence each other on lag 1 and 2, it is mostly. And here also the simulated data in red match the original data quite well. And when you look at it in another way, like the cross spectral density function, you see also that it behaves quite well. So this might be an option to generate artificial uncertainty, but more related to the original data for your MSE simulations. So in summary, the steps to prepare environmental data for explicit considerations in MSE is like to choose adequate data for the history, which can be complemented with available time series of future climate change, which I talked about also in my previous talk. Then bias correct the projection to match the mean and the variability of your history. And you can address the future climate variability uncertainty by generating, for example, a new stochastic time series that behave in a way that the original data behaves. Otherwise, and move on and go to the practical. So yeah, the practical you find also on the SharePoint. It's called bias correction tutorial, and there's also another one called B-bar. This tutorial is rather computational intensive because like calculating the quantile maps takes a bit of time to do it for each grid point. So you can try to follow me as much as you can, and when the specific step comes, it takes more time, then I will just move on my own, maybe, or we just all move to the HTML. Let's see how I will do it. In case you haven't installed all the packages, and do it, and then reload all the packages, and download the data, which is on my Figshare. And this is like a temperature data set, also the Ahoy bottom temperature, then the Polkom's Ersim RCP45 bottom temperature, and the Polkom's Ersim 85 bottom temperature that we load into our workspace, and also define some functions that will help us remove the trend and display some of the variables. So a min-max scaling function and a get trend function, and here also the function that does the heavy lifting for the quantile mapping that takes in a matrix of your observations and your predictions. So observations are historical time series, and predictions are your projections and the different time periods, and then you specify the number of CPU cores to do this quantile mapping, and then this function does everything for you. It's a wrapper function around the QMap package, which here does the fit Q mapping and the do Q mapping, yeah, which basically is implementing the algorithm. And yeah, that's it on helper functions. We just build those, and we do the same as we did for the other tutorial. We do some pre-processing, like removing some areas that we are not interested in, like the Irish Sea and the Kattegat, and yeah, also the landmass cropping. And yeah, we do it for all three data sets, for the historical period and for our projections. I'll also resample it to the same resolution because the Polkom's Ersim data is, I think, has a bit higher resolution, 0.1 something, or yeah, maybe just 0.1. And the Ahoy data has a lower grid resolution, so I resample those to have the same resolution. So you see the data here. And yeah, right, bottom temperature, and then Polkom Ersim RCP 45 and 85. And then those data sets do not perfectly match each other. So some grid points of Ahoy are not available in Polkom's Ersim and vice versa. So you see that there's a bunch of data missing in Polkom's Ersim because maybe I accidentally cropped it. But you see it in the HTML file anyway, right? What comes out of this chunk. And you really need to be make sure that they have the same spatial grid points, right? Both. So when we have done this, right, yeah, here, it looks like this. And here in green, there are some points in the on the coast of Germany and Denmark, which are available in the Ahoy dataset, but not in Polcom AirSam, and others are available in Polcom's AirSam, but not in Ahoy. So yeah, you just crop it to represent, have everything represented. And then we do the mean bias correction, where we pick the times of the data sets and get the overlapping period, and then we calculate for each month we remove the mean bias here in this loop. This also takes a while. I just print out the months to the console, like, yeah, now it's running January, and when this is finished, we can check our bias correction if it worked correctly. This step is also easy to put in a wrapper function and parallelize, because it does it for every month sequentially. So, but I haven't for demonstration purposes. Yeah, this is running a bit, and we can just move on to our next chunk where we check the bias correction. Therefore, I just switch to the HTML because easier. Right, so this is like our uncorrected data. Here in gray, your historical time series, and in red and greenish, your RCPs. And you see the small bias, and when we mean bias correct the data, then the bias is more or less gone, and they overlap. And yeah, that's okay. And when we calculate seasonal means, what we do here now for periods December, January, February, March to May, in summer and in autumn, we calculate mean over those months for all those data sets and look at the bias corrected time series. And we now see when we remove the bias, it's gone for all those different periods where we average the data over. So this is quite nice. And you also see that for a projection, you can't really expect to match the interannual pattern, because, like, as you see, the red curve and the green curve, they are different what you see in the overlapping historical period. This was our data beforehand, uncorrected. So you see there's a strong bias, for example, in summer and in autumn. So we removed this with this procedure. Okay, now we are finished here. So yeah, I just run the plotting again that we already looked at. And now we go to the quantile mapping procedure, which is a bit more complicated. And so, yeah, I explained this procedure a bit here, also the different steps that I apply. And here we do our quantile mapping. So here I do, I convert it to the spatial data, the raster file I convert to a data frame and remove all the grid points that are in A, so lie over land. And then I get the coordinates from my my raster file for putting the raster back together later on. That's why I do this procedure I do for the Ahoy data and the Polcom's AirSam for RCP 4.5. Then I transform those matrices so that the I think then the spatial grid spatial grid representation is then in the rows, and the temporal is in the columns. Oh no, the other way around, sorry. And then I detrended it, right? I detrended per spatial grid cell, so per column. And then I have no trend here. And then I look at the mutual overlapping period, choose a specific time period, and then I remove the trend for this correction time period, again for the Ahoy data, and calculate the mean bias in this correction period. And then I look at the quantile distribution, or the empirical cumulative distribution function, what they look like for the Ahoy data set and the Polkom's-Asam data set. You can see the shape is quite identical, which suggests that we don't need to remove much or correct much for the variance, but only the mean is different. So we only shift the Polkom's-Asam data set probably to the right to match the ECDF of the Ahoy data. And here I do the heavy lifting with the Polkom RCP for 5 data sets and do the quantile mapping. As you see, the observations is the historical time period. So the Ahoy data set with no trend, then the prediction is the projected matrix also with no trend, then the time period which I base the correction on is the overlapping period. And no, I just pass in the old times here, I would say. And those are function arguments that are passed to the internal quantile mapping function. And then when we calculated this one, we can add the trend back on. So here, I remove the mean bias, right? And then I add the trend back on and calculate the quantile mapping. And this is it for the RCP-45 dataset already. So, and this is a comparison for the average bottom temperature. Here in blue, you see the raw the raw projected 4-5 time series, and here in orange and in purplish, you see the quantile mapping and the mean bias correction, and they're almost the same, although the variance of the quantile mapping method is a bit larger than the mean bias correction. This can be because what I explained in the talk was a bit different than what I did here in this tutorial, because this was a bit learning by doing, and here I did not remove the trend of the mutual overlapping period. So this would be here, and there's already a slight trend in the historical period. So if you would remove this one, it would probably result in the same quantile mapping procedure. So you really need to be careful and tweak those steps a bit to really get a meaningful variance out of it, and also meaningful trend. And we do the same, also the same steps on the RCP-85 scenario. And this also, similar ECDF. Again, we look at it, perform the quantile mapping, and get time series out of it. And as you see here, it's the same. The variance of the quantile mapping is a bit different than the mean bias correction, but the mean bias is correctly removed, and also the trend is preserved nicely. We can now look again at the monthly aggregated time series when we do it over the seasonal seasonal pattern. Here I do it and calculate those seasonal averages, and we see that the trend is nicely preserved and also the bias is corrected appropriately. And again, for the removal of the trend here, the mean bias in the RCP85 scenario. Yeah. And then I just write everything out to the disk and store it. Here I do it in a R data format, but you can also write a TIFF file, which is a native raster file, which you can also open then in QGIS or ArcGIS, which is quite nice using the raster or the Terra packages. Okay, here in SST, or no, bottom temperature, sorry, the difference in the variance was not so big, so quantile mapping in this way didn't make much sense. You would also be completely fine with just the mean bias correction, because there is not much of a variance change in the projection period. But what if you might have a variance change? And therefore we move to the zooplankton example. This is like zooplankton data that are already aggregated over the CPR areas for the historical data set. And this comes from the CPR, so the continuous plankton recorder data set. And I calculated a specific index here, zooplankton carbon, trying to match the stuff that I have had available for the projection, because in the projection, in the Polkom's-Erzim data, you only have zooplankton carbon available and some specific functional groups. But I thought, zooplankton carbon in the aggregated index might make sense. So we load this now in and reshape the historical data a bit to what? Okay. And now we again crop our zooplankton data with the mask we created earlier on to remove the Kattegat and Irish Sea and also the land mask. Then we have the time here for the zooplankton Polkom's-Erzim projections and the CPR area names, right? So, and then we can plot those things and overlay the CPR areas with the projection data and can look at it, how those CPR standard areas and the projected data would align in space. Okay, this is what it looks like. So this is the CPR standard areas where which are used to calculate those aggregated averages of zooplankton carbon. And here the colored part is the zooplankton projection data. So here I don't have any data, and also I cropped a bit here, so it's not perfectly matching, but I think it's okay for demonstration purposes here. And yeah, here I just got again some data, how it will look like when I crop the yeah, here I do the cropping of the Polcoms LM RCP 4.5 and 8.5 with the CPR standard area. So I get a specific, is it already? Yeah, just the projection data cropped to the different standard areas. And then I calculate the annual means over those standard areas. And then the units are also a bit different. The unit for projection is mole per cubic meter. We need to convert it to molarity of carbon. So here's a conversion factor. Yeah, this is what I convert. Okay. Okay, here it goes through all the different standard areas and does the spatial masking. Actually, the script still uses the mask function of the raster package, which is rather slow. I would possibly advise to do everything in the Terra package with the yeah, basically the raster package, but the new developed version. It's called Terra, and it's much faster. And yeah, here I just have old code, so it's a bit slow. Yeah, but what comes out, I can switch to the HTML if you want to see it again. It's like here the cropped areas. Here in B01, it's along the Norwegian Trench. B02 is northwestern North Sea. B04 is above the Orkneys. So yeah, and then I just calculate the annual means here. So because we want to bias correct things, and yeah, when we perform a mean bias correction, we see that we can do it, yeah, but since the variance does not really match of the projected data with the historical data, which might also be that the projected data does not include all the different zooplankton types that the CPR data includes, and this is also some aggregated yeah, biomass in the projection. So might be also due to those cases that the variance might not match. But anyway, this is a problem when you project things, and you need to really correct for the variance here. And you can do it very nicely with the quantile mapping. And as you can see, yeah, here's all again an output of the density functions for the historical period in red, the RCP 4.5 mean bias correction in green, and the raw data. And when you see that it works quite well, right? For the area C01, your original raw RCP data was way above the historical period, but the mean bias correction shifted it so that the means do overlap quite well. However, the variance here, as you can see by the spread of the densities, is not really matching. In more extreme case, would also be D03 here, right? So it's not really capturing the variance structure. And therefore, we do the quantile mapping, which here I do not use the wrapper function, which does the quantile mapping per grid point, but I use the original functions coming out of the QMap package, fit QMap and do QMap. And there, I do again the quantile mapping with all the steps involved. First, removing the mean bias and the trend removal to preserve the trend also in the projection period. And then what we get here is way better. So as you see, the RCP 4.5 and 8.5 in B01 first were having a lower variance than the historical record, and were lying also above the historical record. Whereas when you correct for both the mean and the variance, they continue quite smoothly now. And one thing to say also here is that you have quite some different variance in the historical record, right? So one thing was, okay, should I really match the variance of the RCP scenarios to the variance of the whole record, or should I just move the use the overlapping period? And here I decided more or less to use the overlapping period because as you can see, from 2000 on, the variance for a lot of those regions really decreased. And it might be that this continues also in the future. I'm not really familiar what happened there. I need to read the literature, but might be also related to the regime shift in the North Sea and specific zooplankton species being declining, so that also the general zooplankton carbon declined. And therefore, I would advise to correct or choose a correction period to appropriately match what is known about the system and what might happen, or what already happened in this system. So that's it for the quantile mapping. I just plot the densities again here. And as you can see, the densities of the corrected data in green and the historical data now match certainly much better than before, thanks to quantile mapping. And now we write this again out as an R data file, for example, for later analysis. So that would be this tutorial. Any questions on bias correction?
I don't know if I understood it correctly, but when you do this detrending things, is it always a linear trend that you fit to, or can you do a more, for instance, GAM model type fit?
In this case, yes, I removed the linear trend. You can also remove other trends, but I would advise to keep it monozone, right? So monosonically increasing or decreasing and not having a wiggly structure. Although, like for salinity, which I didn't show here, I removed more or less a more wiggly trend because there was like some large scale oscillation happening in the projections, which was not really happening in the historical part. And having a large scale oscillation is was increasing the variance a lot, right? And not accounting for that, would result in a very high variance. So you needed to correct also for that. So yeah, it's possible, but it should also be yeah, I think just throwing a GAM and not constraining it, K, right? For example, the degrees of freedom would not be such a good idea. I would always constrain it to some, so that it has a yeah, more constrained behavior. So yeah, as I was saying in my previous talk, this procedure is to generate artificial time series with the same stochastic properties as your original projection data to have a bit yeah, more Monte Carlo simulation and to put into your MSE simulations. Here's a short introduction in the HTML you can find on why to do it. Here again, the required packages. And again, we load the packages. Again, you can download the data from my Figshare account, what we do here, but since I ran this already, I have the data already downloaded. We have our Polcoms ASM SST raster, which we use a mean bias. It's already mean bias corrected. Then the salinity raster, which is mean bias corrected, and a current raster, which is also mean bias corrected. So we have those three data sets. And then I have here a function which removes the nonlinear trend. As I said in my answer to Marcus, this is a way to remove monoson nonlinear trend via a p-spline approach and constraining it to either have a monotone increasing p-spline or a monotone decreasing p-spline, which yeah, we also load in. It's a nice helper function that we use later on. And here we first calculate the anomalies of the data. So there we remove the mean for each month, yeah, from every grid point. And then we perform our spatial PCA analysis on every one of those three data sets. And you have salinity, you have SST, and you have currents. And then we select on how many PCs do we want to put into the algorithm. I just selected an arbitrary threshold here of 80% variance explained by each of those three data sets. And this will give us 51 PCs, because yeah, for salinity 14, for SST only 3, and for currents, which is more complicated, 34 PCs. You can also, yeah, try to look on a scree plot or where the elbow is here to select a meaningful number of PCs. But yeah, I just selected this arbitrary threshold of 80% here. And then, yeah, we can look at the explained variance that we get with all those different for all those different data sets. R is particularly slow today, sorry. So yeah, here we just plot the number of PCs and the explained variance and threshold, which we selected, and then we select the number of PCs here, and when this is finished, we can move on and remove remove the nonlinear monotone trend from the PC. Because with the BVAR, we don't want to model the trend really, but we want to model the variability in the environment. So really the stochastic process that's behind it. So therefore, we get rid of the trend first, and then only model the stochasticity with our BVAR approach. This is also quite common when you have a univariate time series. Then this approach is called Box-Jenkins approach. You might have heard of in traditional time series analysis, where you decompose a time series signal in trend, seasonal component, and remainder, and model the remainder with an AR1 process, for example. Okay, now we have all the PCs. 80% is quite okay to get the elbow, right? Okay, then we remove the nonlinear trend and put everything together into a big matrix, which we then pass on to the BVAR process. Here I say something about the BVAR in particular. Some is picked from tutorials from Kushnik and Washold, 2021. Also a paper by Giannone, 2012. They are more in the realm of econometrics. So there, this method is quite often used to model economic variables. But I figured this can also be, as this is an extension of an AR1 process or AR2 process, just in a multivariate way, this can easily be applied also in this situation. And the whole process is about modeling your current state, your current time series state as a sum of previous states you were in of this exact variable, and also of lagged influences of other variables. And to really fit a stable model here, you define some priors. In the realm of BVARs, the easiest prior to use is the so-called Minnesota prior or Litterman prior, which imposes a restriction on the coefficients. This gives more importance to lags of the recent past from your own variable than from other variables. Oh no, giving more importance to lags of the recent past than at earlier times for the variable's current value. Yeah, right. So recent past has more influence on your current state you are in than the past values that are more far away. And also the autocorrelation is much more important than the cross correlation. So the influence of the variable on its own is more important than other variables on the variable. And then you can define those priors. Here's some more theory. And here with the code, I define those priors, which I just took from the tutorial of the BEVA package, more or less, as a first guess. And then when we have those priors defined, we put this into the BEVA procedure. And here you see it gets fitted, takes around, depending on your model, takes around 2 to 4 minutes for this particular data set. When you have more PCs, more than 51 PCs, of course, it takes much longer. And here we only fit a model of leg order 1, so only legs, yeah, of the last year can can influence your current year. And when this is done, we check for convergence of the algorithm. This is done via a series of tests. They suggest here a Gießecke diagnostic, which looks at the convergence of the Markov chain, Monte Carlo simulation, simulation. And if the value we get out of here is indicates convergence, then we are good to go. Right. So yeah, here we have run our BVAR, and now this is what comes out. Standard. This is a standard diagnostic of this package, and we can just check if our model converged with a diagnostic, with a G-vector plot, and all those points should be more or less within those bounds to show convergence. Those are outliers here, but I guess in general it looks quite okay, and the Z-score is also okay. And then when we have a BEVA model, we can generate new trajectories. And this is done in this way. So we get our coefficients out of the BEVA procedure and the variance-covariance matrix. And then we can put it into a simulation function. Here I just plot the different coefficients and the variance-covariance matrix. Still running. We can now just simulate new trajectories, just maybe 100 realizations, and check their behavior by comparing them visually with an autocorrelation function and with cross-correlation functions, and see if they match to each other. And so there I sample a starting value. Here I sample from the whole, just one starting value from the trend removed time series, and put it into the function var_sim, which is from a different package. I think it's from TS_dyn package, and not the BEVA package. And there I put into the coefficients, the variance-covariance matrix, how many steps I want to simulate into the future, then the leg order and the starting value. And then I just run it and see how it looks like. And this is for I think it is, let me check the code. It's salinity. And here you see, okay, the bounds of the simulated data are okay, and the original data is within those bounds. And then we check the autocorrelation function. Yeah, I think the autocorrelation function was already calculated here, but here we plotted and see how those overlap. And we see here, so in gray, the observed autocorrelation function, and in red, the simulated autocorrelation function. For higher lag orders, it overestimates a bit the autocorrelation, so it's not as fast declining as the original observed data, but all the points of the original ACF lie within the bounds of the simulated one. So this is quite okay, I would say. I think there might be room for improvement, but for the moment, this looks rather good. So we take our simulation, add back the trend, and then we have everything back. But what we haven't seen or looked at is the cross correlation, and that's what we want to look at now. It's quite hard to look at 51 times 51 combinations. So I just show a couple of them. Yeah. Okay, here, okay, it took approximately 7.5 minutes. This BEVAR procedure, BEVAR model fitting. So yeah, not 2 to 3 minutes, sorry. And then you can plot all the stuff, and we are back on our R script. Okay, generating the ACF also takes quite a while. So we might be better off here in the HTML. So yeah, here I try to calculate the CCF, the cross correlation function, for various combinations. And plot those. And also calculate the cross-spectral density, which is like the same as the CCF, but only in the spectral domain. And yeah, I plot all these different types and combinations. Here I only picked out specific ones, but here you see the cross correlation function, for example, for PC2 of salinity and SST of PC1. They have quite a unique cross correlation function, which is very well matched also with the simulated data and also with the cross spectral density. Here, the currents PC9 and the salinity PC12, they do not have much in common because the cross correlation function is rather flat, and therefore but it's also correctly integrated in the model. And here you have a specific lag 0 correlation of salinity PC1 and salinity PC2. And it's also correctly attributed in the cross spectral density. One could think about a test, which I explain here, but yeah, since I haven't got the time yet to do a test and to implement it, it's just an idea. So maybe if you have time and feel confident, you can take this as a first idea. And then when we looked at various spectra and different autocorrelation functions, we can then reconstruct our new spatial fields from this from the simulated PCs. So here I get like the simulated data and like the simulated PCs, right? And then we have the remaining PCs that we didn't include into our process. So we add those back into our modeling procedure to reconstruct the environmental fields. Here, I rebuild those fields by using the loadings of the PCA and doing a matrix multiplication with the, I think, the scores coming out, right, or the PCs. And then we have we have our original matrices built back up, and then we add the coordinates, and then we generate the rasters with the coordinates and the grid points. We generate those new raster, and then that's it. We have reconstructed a spatial field, like our salinity field, our FST field, and our current field. And then we want to look, okay, how would a PCA on the simulated data would look like? And we can compare it to our original data. And that's what I do here. We have 5 minutes left, so I will just quickly go over it. So yeah, the simulated EOF pattern is closely related to the original one. Yeah, there are some discrepancies, right? But also the PCs, the original and the simulated ones look quite okay in terms of stochastic behavior. Here's again a comparison of the salinity signal, and I compare the different PCs and the autocorrelation functions again. So a lot of comparisons, if this really makes sense in a way. And I would say it does, because the shapes of the ACFs look quite similar. And yeah, we do it for the temperature as well. So salinity we checked. Temperature looks quite okay. The spatial decomposed pattern also look quite the same here for PC1. The trend is also preserved because we removed it and added back on, so it should be. UF2 looks okay, although the border here is a bit different, and so on. And what you see, those have some discrepancies, and then you see, okay, UF4 is like perfectly matching, and UF5 also. Why is it? Because we only put PC1 to PC3 of temperature in our algorithm. So of course it should match perfectly, because the decomposition should be the same of the higher order EOFs here. And it is. And again, we compare the spatial averages or seasonal averaged signals, and then do it for currents, last but not least, and also looks quite okay-ish, I would say. And that's it. And this is the procedure. Sorry that I went over it very quickly. In a quiet moment, you can go over it by yourself in more detail, and you can also write me an email if you have any questions. And for convenience, I build a SEAwise wrapper function that is depicted here, which does all those different pre-processing steps all in one function, and gives you back the simulated field, which is quite convenient. Although no, it doesn't give you back the fields, it just fits, sorry, the function fits spatial BVAR, does the fitting procedure of your BVAR, so it decomposes your data into PCs and does the model fitting, and then your second function, sim spatial BVAR, is simulating from this particular fitted BVAR model and creates new spatial fields. How many you want, 100, 1,000, whatever. And it's parallelized, so it's also has some C++ code. I would, yeah, here, so to make sure it's not super slow. It's slow, but not super slow. And here I just apply it and fit a spatial BVAR with a wrapper approach, and then what we get out is like our salinity anomaly looking good, our SSD anomaly, and our currents. So yeah, that's it briefly and very fast. Hope you still get a glimpse of the main important concepts, and yeah, feel free to go through it by yourself again.
Started going down this road of generating new forecast data. I think we were seeing very few examples in the literature of people doing this. They might just use a single iteration and create all of the noise around a given future forecast due to other parts of the model, not due to the underlying climate signal. Now that you've seen a bit more of the literature, do you still think that that's the case, or do you see other literature that's also doing something similar to what you've done?
From our workshop, the WK EcoMSE workshop, what I saw there where people did a lot of like incorporating autocorrelation also, and trying to simulate also regime shifts and things like that, but not really using pre-made projections, but more doing the data poor approach that Marie was talking about earlier. And I mean, like what people normally do when they have a lot of manpower, I would say they use a lot of climate models, right? So they use ensembles, for example, and then they have everything in there, but you might not have ensembles, or you don't get your hands on ensembles. So you might just have this one time series, and then you go forward with this approach maybe. And I haven't found so many examples doing those kind of stuff that I did. Yeah.
Okay, so I'm going to talk a bit about fitting growth models. And the topics I will cover is that annual variation in growth increments is what we're looking at. And we're going to talk about scaling environmental variables for model estimation. I know Bernard just went over scaling environmental variables for the future and making projections into the future. And that's a different process than what you need to do for model estimation. And when we were doing our collaboration, it caused a disconnect in the data, but Bernard solved the problem. And it's possible to do that just by rescaling the variables. But I'll get into that a little bit. Then I'm going to show you how to use linear mixed models of weighted age and how to fit some mechanistic models of length at age and use AICC for model selection. Just an introduction, but then Mark will also talk about model selection in a variety of ways tomorrow. So you'll just have a little introduction to that. So here we're looking at weighted age as a component of productivity because the stock has these variable weights at age that go into the SSB. And what you're looking at is a timeline of the weighted age for a stock. I believe it's haddock that has 6 age classes. The 6th is probably the plus group, if I'm not mistaken. And you can see that it varies, especially for these older age classes. It varies with time. And we're wondering if that productivity is the result of some process with the environment, like temperature causing a higher metabolism that Olav talked about, or it could be density dependence, that sort of thing. So we want to see if we can model this weighted age through time. One way of looking at this that's been done historically is these Ford-Walford plots. So you can look at the x-axis is weight in year t, and then the y-axis is weight in year t plus 1. And this dotted line is the 1-to-1 line, which means they're staying the same size. And so people in the past have used this to estimate what L infinity would be just by eye. You can assume the L infinity is where they reach stasis. So their weight in 1 year is equal to the weight in the next year. But on this graph, you can see that there's a lot of spread around the pattern, and they do shrink sometimes. Their weight, well, not weight. I said L infinity, but I meant weight infinity because we're looking at the weight graph. Yeah, weight infinity doesn't really exist because they shrink, and there's a lot of variability around that process. So it's not just one number, but it's convenient to model it as one number. And we're going to look at the variability around that and what's causing variability in that process. So one way to think about it is looking at these Ford-Walford plots with extra dimensions. And I divided up the data into 2 groups. One where the temperature is above the mean, that's the red group on the right, and the other is the temperature below the mean, that's the group on the left. And you can see that on the left, growth is slightly higher than it is on the right, and that's because of the temperature dependence of this growth process. And yeah, that's just one example. So what we want to do is model these annual growth increments. The environment varies, so the growth rates also vary. As you saw in the last plot, they were varying by temperature. So we'll model the length or weight as a function of the length or weight in the previous time step. And it's t minus 1 if the time step is 1 year, or it could be t minus delta t if you're looking at some continuous model where you can have continuous time steps. But for the examples today, we're all looking at annual time steps. And then the size, length of t, or weight at t also depends on the environment. So I think you can see my cursor. Yeah, it's a function of both the previous size and the environment. And it's easier if you scale the variables to the average environment so that those predictor variables have mean 0 and standard deviation equals 1. And I have a citation on this that I'll add. It applies to most demographic and ecological modeling because it allows a clear interpretation of 0 coefficient estimate. That means that you have 0 effect. So a deviation from the average environment means nothing for that if there's a 0 coefficient estimate. And it's also better for some of the estimation algorithms. They have better convergence properties. And just a side note, we omitted the plus age group because it is a time-varying mixture of ages, and we didn't want to confound the time-varying environment with the time-varying mixture of ages. So we just subset that out in all the analyses. The simplest way to model this is with a linear mixed model, which many of you are familiar with. You might be familiar with doing this in LME4 or GLMMTMB or many other packages and many other softwares. But if you're doing it in LME4 or GLMMTMB, this is the formula interface, the formula syntax that you would be familiar with, perhaps, where the random effects are written like this, and the fixed effects can be written like this. And what we're saying here is our response variable, log weight in the next year, depends on log weight now and the temperature this year. That's the fixed effects part of the model. And then the random effects here, we're saying this random effect of year means that the intercept varies by year. There are good and bad years. So for all age classes and for all cohorts, there will be years when they're all above average in their growth rates and years when they're all below average in their growth rates. That's affecting them all in some way. And then we also have this random effect of cohort. That means the intercept varies by cohort. So some cohorts have a lifelong advantage, maybe because they grew up in low density and plenty of resources per capita, or some of the cohorts were born at high density and they have limited resources and they'll have reduced growth rates for their entire longevity. Yeah, and we assume that these random effects are on average 0 and have a normal distribution. That's just the simplest assumption for the year effects, and the same for the cohort random effects. And I'm not going to talk about selecting from the random effects because we're just keeping them in there as part of the observation design. I'm assuming that growth always varies by year and by cohort as a baseline assumption that I'm not even going to test. So for more flexibility, we could make the formula more complicated. And I arrived at this formula by just trying lots of different things that seemed to make sense. But basically, you're saying log weight in the next year depends on log weight this year, plus age, plus how log weight interacts with age, plus there's a quadratic effect of age and a quadratic effect of log weight, and those also interact here. And then here we have our environmental variables. Salinity.s is sal.s is salinity scaled to have mean 0 and standard deviation 1, and ssb.s is ssb scaled to have the same, and the same for temperature.s. It's scaled temperature. And then we have a quadratic effect of temperature to check if maybe there's an optimum, and some other interactions. Log weight can interact with salinity, and log weight could interact with SSB. The idea of this is that depending on the weight of a fish, if they're above or below average weight, they might be more robust to the effects of the environment. So that's what the interaction terms do. And then we still have those random effects. And I should say, the reason why we're modeling log weight instead of just weight is because using a log normal assumption for weight makes sure that weight is always positive, and that makes it convenient. Yeah, the weight the weight predictions will always be positive, but they can still shrink from one year to the next. Like you saw in the Ford-Walford plot, they shrunk. Okay, so here's another Ford-Walford plot with some model predictions that included age and SSB and temperature in the model. And so each of these little groupings is an age class. Here we have age 0, and age 1 and age 2. And as they get larger, the age classes sort of blur together. But you've got weight in 1 year on the log scale on the x-axis, and then the y-axis is weight in the next year. And these young age groups are growing quite rapidly. And then the older age classes get closer and closer to the 1-to-1 line because their growth is slowing down. And the extra dimensions we have displayed are the SSB is in the left panel. So red is a low SSB, and green is a high SSB, which is, yeah, so the higher SSB is closer to the 1-to-1 line and therefore a lower growth rate, as you'd expect from density dependence. And then on the right is temperature. The higher temperature, in this case, for these young age classes, the higher temperature is giving a higher growth rate. And I don't know this exact species very well, but it's interesting that the pattern switches. And then for these higher age classes, the lower temperature is better for growth. A higher temperature reduces growth. And some of them shrink, as you can see. Yeah, so that's what you're seeing in these plots. Okay, we could simplify the model by doing model selection on the fixed effects. So you've got this whole complicated global model here that has many terms, and some of them might be useless. Like in the previous plot, there was no salinity. That was not included in the model. So how do you know what's the best model? So we're going to simplify this model. We'll keep the random effects to avoid pseudo-replication. That's what was pointed out by Hurlburt. I'll put that citation in there. As a starting point, you could use AIC to select the best predictive model. It should give the best predictive model, assuming that all correlations are accounted for, but I found that that's not actually true. There are additional correlations, and therefore the models I select by AIC or AICC or anything, it's not necessarily the model that gives the best extrapolation, which is interesting. Yeah, but that's a bit complicated. In general, you can use AIC and you try to get the best model, but it doesn't always give you the best one. BIC is sometimes used to get an even simpler model, but is intended for cases where you think the true process is represented by one of the models you're selecting from. And in biology, that's usually not the case because the real world is much more complicated than our processes for modeling. You know, all models are wrong. But some people like BIC because it gives you a simpler model in the end, usually. And then the third option I'll talk about is AICC. It's the AIC corrected for small sample size. And as your sample size gets larger and larger, this gets closer to the AIC, that's the original AIC. So it's generally a good choice. It penalizes the parameters. If you have more parameters and not enough data for those parameters, then there's more penalization, and it'll encourage you to select a simpler model because you don't have enough data for a more complicated model. So that's usually a good thing. So that's what we'll use here today. Yeah, to select from all subsets of a global model, you can use this dredge function from the MuMin package. It will do it automatically quite easily. And you choose the information criteria that you want that function to use. I'll show you this in the code. And then we can use this broom mix tidy function that will extract the estimated coefficients with their confidence intervals. And that's useful for just looking at the effects, the magnitude of the effects, and whether or not they're overlapping 0. But you should be aware that the confidence intervals will always be too narrow, and p-values will be too low after model selection. So if you do AIC to get the best model and then you look at the confidence intervals, it's still an interesting thing to look at, but you should know that the confidence intervals are not really 95% confidence intervals. They won't have the right coverage in the frequentist definition. So now let's look at this code in LMM haddock example.r. I'm using the GLIMTMB package to fit the linear mix models just because it's familiar to me and I use it a lot. The MuMin package is there for the model selection. I use this broom mixed for extracting coefficients, as I said. I'm loading this data set that I'm distributing to you all, and it includes this object just called DAT, and it's extracted from a FL stock object. And so it's information that you could extract from your stocks if you had them, or any population you had. But basically, you can see that the increment is annual. The growth, we're observing annual growth. And so we've got all these cohorts, and they're measured every year from one age to the next. And there's no missing data, which makes it quite convenient. And we have these variables, SSB, temperature, and salinity. Those were extracted by my collaborator, and it was, to the best of our ability, it was the relevant spatial scale that we aggregated over. Yeah, but depending on your specific stock or population, you would choose the right variables. And those are on the annual scale. We've aggregated them to just have one observation per year because we're trying to model growth from year to year. We also have the observed weight in one year and weight in the next year, and that's what we're going to model here. And I'll show you that. But there's other variables we could have included, like N, I think, was stock number. And we're not doing an exhaustive analysis of all possible covariates. Like there could have been initial cohort size and things like that. But just we're checking for the relationship with SSB, salinity, and temperature. So I take that data that we just read in and transform it. So I'm taking a subset where I remove the plus group because of that time varying mixture of the ages. And I'm putting the weights on the log scale just to, yeah. So then I'm using the scale function to change the SSB and salinity to have mean 0 and standard deviation 1. But to be able to do the processes that Bernard showed you, you have to save what the mean and variance were so you can get back to the original scale. It's just good to save those. And I haven't done that in this example, but you would want to in a real study. And then I'm changing year and cohort to factors. Just, well, sometimes it's useful, but it's not necessary in these functions because GLIMTMB will always treat your grouping variable of the random effect. It's always treated as a factor. Okay, so we transform that data, and then I'm fitting this simple model here where log weight next year is a function of log weight plus age plus salinity and SSB and temperature and those random effects. And since I don't say anything about the family, then it's automatically a normal distribution. And so it's assuming that log weight is normally distributed, which means weight would be log normally distributed. And I'll talk about the details of that distribution tomorrow, but it seemed like too much mathematical complexity to talk about today. So for now, just note this means weight is log normal. So we fit a simple model, and then we can get out the model estimates with confidence intervals, and these will have the right coverage. These confidence intervals have the right coverage because we haven't done any model selection yet. So here, the interesting parts are the first three, the top three. Those are the environmental variables. Temperature is definitely below 0, so that's saying there's a negative effect of temperature. Having a higher temperature will give you a reduced growth rate. And then SSB and salinity are both overlapping 0, so it seems like there's no significant effect of those. And then these log weight and age, they're not really interesting. They're sort of just the backbone of the model, but it's really these mediating effects of the environment that we're more interested in. And so that was one model, but then there's lots of models we could consider. And so I'm going to do model selection where we can consider all subsets of this global model. And the global model is the one I showed you before that's quite complicated. The backbone of it is all these terms here, the weight and age combinations of terms, the interactions, and then the environmental effects are these terms. Well, yeah, all these terms are different environmental effects. And so some of them might drop out, but some of them might be included. When we're doing the model selection, it always will keep these random effects in there by default. So first we fit this full model. This is the formula. I put the formula into an object called full form RE just to keep it a little bit cleaner. And then I give that formula to the GLIM-TMB function and it will fit that. And to be able to do the automatic model selection, you have to also tell it to fail if there are any NAs, because when you're doing AIC model selection, it has to always be done on the exact same data set. And if there were any missing covariates for some years, and those got dropped out of the model sometimes, like, for example, if there was some missing salinities, then if we didn't have this command, the models that didn't include salinity would include the data that has missing salinity, but the models that include salinity would have to drop the observations that had missing salinity. So this just makes sure that if there's any missing data, the model will fail, and you have to be careful not to have missing data so that you're always selecting from models fit to the exact same data set. Okay, so that's our global model that we then dredge. We fit all subsets of the fixed effects, and we'll look at an AIC table. That's what this dredge function does. And we're ranking them based on AICC. This takes a little time. It's also possible to do it in parallel, and I might do that in the code I get you to run tomorrow. So I'm going to get you to redo this tomorrow, and just in case anyone has a slower computer, then I think it would make sense to do it on a cluster. Not a cluster, but like just in parallel. Okay, Marcus?
Yeah, one question. I didn't quite understand. Since you reduced the growth, so to say, to one number per year, right?
Well, there's each cohort has one observation per year. Yeah.
Maybe you said it, I just didn't understand it. How is the interannual variability? I suppose there must be different variability between years. So is this accounted for somehow? Do you understand the question?
You mean? No, I don't know that I understand the question.
There would be some of the years where you're more certain about the growth than others.
Oh yeah, you mean the cohort size? Yeah, there could be, because in some years you collect more weight observations to estimate that cohort's average weight. Is that what you mean?
Sure.
Yeah, I did not account for that at all. That is a good idea. I think that it would be straightforward to add an argument a weight on the log likelihood. Yeah, that seems like a good idea. If your stock had highly variable uncertainty in that, then it does make sense. Yeah, and this function has a argument. You could say weight equals the inverse of the uncertainty on that cohort. Like if you have variability to go along with your weight column, then the model weights could be the inverse of the uncertainty, the inverse of the variability. Yeah, Mark, do you want to say something?
Only that I think in the von Bertalanffy model that we fit, we used the numbers at age as a weighting, or the log numbers or something like that.
Huh. Was it the observed numbers at age, like the ones that were actually in the sample?
I think it was that was reconstructed with the assessment. So it's not a perfect fix, but I guess my idea was that it's probably related to how many samples you would expect for each of those ages from a survey.
Yeah.
But yeah, it's I think ultimately if you had the information on how many individuals were sampled for that weighted age estimate, you could use that directly as a weighting. But we didn't have that.
Yeah, that would definitely be possible to do. It's very straightforward. But I could talk you through the next steps. So when we get that object, the D tab, we're going to look at the AIC table, and it ranks all the models by the AICC. So you can see what coefficients were in the top models. And then we will take out the top model, the very most parsimonious model, and we will plot the coefficients from that model with the confidence intervals, but they don't have the 95% coverage. Okay, so now that's done. So we look at the top models here. If I was doing this for a report, I would put this in a better format, but I hope this isn't too terrible. So what we're looking at is the top of the AIC table, and it's saying that we'll ignore, like, these are intercepts. Of course, every model has an intercept. Every model has an age effect and an age squared effect, and log weight and log weight squared. But then where it gets interesting is these columns that represent the environmental covariates. And you can see that all of the top models had an SSB effect in them, and it was always negative. So that means SSB decreases their growth. And also down here, the temperature column is always filled in by a negative number, which means the temperature always had a negative effect. Here, the salinity column, sometimes it's blank, and that means that the top model did not have that coefficient in it. That dropped out of the model. For most of these, it dropped out for the top two. There was no salinity effect in the top two model, and then no salinity effect in the fourth and fifth top model. So salinity is way less important for this stock than SSB and temperature. And then the interaction terms are kind of interesting, but kind of harder to interpret. There's a interaction with log weight and temperature. So higher weight means an even worse effect of temperature. And then there's this interaction with log weight and SSB such that the sign could change. For a higher weight individual, maybe SSB is not that bad. The smaller individuals are suffering more from SSB. And the plots, like I showed you in the example, that would make it easier to see this rather than just interpreting the coefficients. But the way the AIC table is set up is using the delta AICC. And of course, the top model is the one that you're using as a reference to calculate the delta AICC. And so it always has 0. And then the others are the models are organized so they're worse and worse, but none of these models are actually that bad. That's not a lot of delta AIC. And the AICC is meaningless on its own, but we could compare it to the mechanistic models because we're always modeling, well, no, actually, only if you're modeling the same response variable of log weight, then you could model the AICC. But for the mechanistic models that I'm going to show you later, we have a different response variable, so you can't even use the AICC for anything. Okay, so then we could plot all those coefficients in the top model that we got. Okay, so you can see the environmental effects are this strong effect of temperature that's negative. And then SSB is overlapping with 0. There's that interaction of log weight and temperature. And then the other terms are not very interesting. They're just the growth, the backbone that's log weight and age. So that is that for the linear mixed model example. So I wanted to introduce you to some mechanistic growth models that Mark Taylor found in the literature. But basically, we converted the weights to lengths, and we used just the 2 coefficients A and B that are pretty standard, and we didn't look at any time variability in those A and B. And so any variability that's in A and B will go into this other part of the model. And it seems to work out okay that way. Even though it's inaccurate, it's still like the error has enough places to go in this other part of the model that it's fine. So we're modeling lengths, and we modeled the annual growth increments using either this Gompertz model or the specialized von Bertalanffy or a generalized von Bertalanffy. And what you can see in each of these, the response variable is the length at time t plus delta t. And it's a function of the length at the current time step and also L infinity and K. Yeah, each of these models has that property. And we're always modeling delta t as an annual time step. So that's a little simplification. But it's nice that these models are flexible. So if you had continuous time observations, if you were in a situation where you somehow could ignore seasonality, then maybe that would be helpful for you, like in a lab experiment. But if you were in a real semi-annual time step out in nature, you would have to account for seasonality, and that's a whole different complication. So we're not going to talk about seasonality here. We're just going to have delta t as the annual time step. Okay, so then the complexity that we added is that in each of the above, we're modeling L infinity using this formula, where it's modeled on the log scale so that it stays positive. This is a trick just for keeping a parameter positive. And this is just a linear mixed model inside of it, where I have x beta is x is a design matrix depending on your formula, whatever formula you want to use, and then beta is a vector of the estimated coefficients. And this is just a flexible framework that's used in all of the linear modeling packages where you that's my cat, sorry. Yeah, so x beta is your fixed effects, and then we're always including the random effects. Similar in the last one, we have cohort and year as random effects. They're random intercepts with They're normal random intercepts with mean 0, and they each have a variance. And for the fixed effects, we selected them from a global model formula where there's an intercept and then the SSB scaled and salinity scaled and temperature scaled. And so I'm trying all subsets of that global model. I'll show you that in the next part. To keep it sort of simple here, I modeled length on the normal scale. I didn't model it on the log normal scale, and that's for complicated reasons that I won't get into. Yeah, and then I converted the predicted lengths back to weights, using the same A and B coefficients as we used up in the first step. Yeah, so you go forwards to the lengths and then backwards to the weights, and it seems to be fine. We got those A and B coefficients from FishBase that I'll share a link for, but if you have them more specifically to your stock, you could use more specific ones. Okay, so I'll show you an example of the same stock, haddock. So here I'm doing, this is the code called LAA growth had example that stands for length at age growth. And I wrote a package using the package RTMD, which makes it really easy to write new packages. Well, actually, technically, I didn't make it a package yet. It's just a collection of functions. But I plan on turning it into a package once it's completely finalized. And so those are in this bit of code called LAA growth RTMB, but if you source that, then you can use it just like it's a package. The only things lacking right now would be help files and documentation and that sort of thing. We're gonna do model selection in parallel because I want it to be fast. Yeah, I should have done that for the dredging. Sorry about that. I will correct it so that those are there. So the parallelization is there. And so I'm reading in that haddock data where I've stored both the data that you saw before and this WAB, which is just a little vector where we have the genus and species and the stock code, and then the coefficients for converting back and forth from length and age. Yeah, you can get those for your stock. You could get them from this FishBase link or wherever you want. And so here I'm using those coefficients to transform from weight to length and from the next weight to the next length. And I also, again, I'm subsetting to remove that plus group like we did before, and I'm scaling the environmental variables to have mean 0 and the standard deviation 1, just like we did before. Yeah, so then I'm gonna fit one simple model using a function called fit LAA for fit length at age. And we'll give it our data, and it will always look for L2 and L. It's just not as flexible as some other modeling frameworks. And then you give it a formula for L infinity, like I showed you here. So we're giving it a formula for how we want L infinity to change on the log scale. So the model formula for X beta. And here I'm using an intercept plus SSB plus temperature. And I'm saying that the model shape I want to choose is von Bertalanffy, generalized von Bertalanffy, sorry. Yeah, I guess I could show you a little bit about this function. So this function will let you use the specialized von Bertalanffy growth function or the generalized von Bertalanffy growth function or the Gompertz. And the way you specify it is with that as a string. And I will put that in the documentation as soon as I can, but it's not there now. But for now, we're going to fit this one. And it's pretty fast because TMB is pretty fast. And then I have this predict function, pred LAA, and it takes your fitted model, that's the GFIT, I call it, your fitted model, and then a new data that you want to make predictions on. And here it's just our observed data because I'm not getting into forecasting yet. This is just predicting back where we have the observed predictor variables and they're all available. So we make our predictions for the next weight. This is using the observed current weights. So of course it's going to be very accurate. And then we predict the weight by scaling back from the length using those A and B coefficients. So we transform back to the weight scale. And then we could plot what that looks like for all the cohorts. So I've colored the cohorts and you can see the predictions are not bad. I should mention that in the predict function, I am not using the random effects estimated. I'm just setting them to 0 because I want to be able to forecast into the future where we don't know what the random effects are going to be, the year effect and the cohort effect, like you don't know exactly what's coming. So I'm making population level predictions unconditional on the random effects. Yeah. Okay, so that's a nice little plot. And then I wanted to demonstrate doing model selection for you. So here's a list of formulas that contain all subsets of this first formula. And this is essentially what the dredge function is doing, but it does it automatically. And I didn't make this current code compatible with the dredge function. So you have to list the formulas that you would like to try for predicting your L infinity. And this intercept only model is just a constant L infinity, which is fine. And then the model forms that we might choose would be these 3 that I showed you in the code here. Those correspond there. And so I'll load those objects in. And then I'll set up a cluster just to make it faster. And then I set up this grid where I say the F is in 1 to lengths of the formula list, and M is 1 to the lengths of the model options. And the way this expand grid function works is it gives you all combinations. So what we're doing is trying all combinations of the formula for L infinity with all 3 of those model shapes. Like that. And so then I use the for each function to fit that in parallel so that hopefully it's faster. Yeah, that was really fast. And I get out, what I'm taking out of these all is just the AIC. I'm not saving the model fits or anything, just getting the AIC so I can rank them. And then I'm looking at which gave me the minimum AICC. And is this model formula combined with this shape gave me the best AICC. Yeah, so we could go back and fit that to the same stock. That's an option, but I won't do that here. Tomorrow we'll do this again with a different stock, but this is just first example. Yeah, so we fit that model and we allowed L infinity to vary by temperature and SSB. But then when we did model selection, it said that it was actually better to just let L infinity vary with temperature. So to recap, we talked about how growth varies from year to year depending on the environment, and linear mixed models and mechanistic growth models can capture this. And I showed you that AICC can be used to select among models. And don't forget that the confidence intervals are overly narrow after doing model selection. So you can look at them, but you have to be aware that they're not 95% coverage. So topics for tomorrow that I want to cover would be making predictions on the real scale from a model that's fitted on the log scale, and predicting with new data. And we're going to apply this to a sole stock also. Like, I was thinking you all could run the code yourselves and ask questions and things like that. Okay, and I thank SEAwise for the encouragement and funding, and all my collaborators in SEAwise that have been great.
Hi, Molly. Just a quick question about the different annual growth model used. So, are there any other type of model from, far as you know? Because we see the Grompet, the specialized, and the generalized von Bertalanffy, but I'm just thinking about other type of growth models.
Well, someone gave me a reference for a weight model that they think might work, but the important thing is it has to have length on the right-hand side, like length in the current year on the right-hand side and length in the next year on the left-hand side, or weight in the current year on the right-hand side and weight in the next year on the left-hand side. And I haven't found models that do that. Well, actually, yeah, did you have any mechanistic models in mind? Because I
Not
know
precisely, because there are many models about growth, so I have some ideas, but I don't know how can be applied, or if they can be applied as well.
Yeah, we needed to be able to be applied to these increments so that we can allow the predictor variables to change every year. Like the SSB is changing every year. So L infinity in this model is changing every year. And that's the flexibility we need to be able to have. I've seen a lot of other modeling studies where they'll fix L infinity. Yeah, assume that it's constant. But we need this sort of flexibility to be able to look at the variable temperature and SSB and the variable environment. Yeah. But then if you want to get out of the mechanistic realm, there are other regression methods that can do this. So we also looked at lasso methods that do automatic model selection, and also generalized additive mixed models. And those perform pretty well, but not much better than the ones I'm presenting here. If those performed much better, then I would present those. And it's just seeming like all the methods sometimes perform well for one stock, and there's not a clear best method.
I guess I'm more used to fitting von Bertalanffy is like not with this sort of incremental version, but where you have just the length as the response variable, and then as a function of L infinity times the bracket with the x and the minus k. So I'm just wondering about how that's related to having these lengths not on an individual like fish level, but sort of aggregated or summarized by year. Sorry, it's not really a question. I'm just trying to make the connection here. But can you explain a little bit why you do it like this by year?
Yeah, partly because this L in the current year, L in the current year, it is the result of all the environments that the cohort experienced. And so they arrive at this current size. They could be above average or below average based on the environments they've just experienced. And so that adds a lot of variability. It can add a lot of variability. And if you just had L infinity on the right-hand side, like K and L infinity, if those were your only parameters on the right-hand side, then you couldn't capture that memory of past environments. I think the standard growth models don't have this flexibility. And yeah, even if L infinity varied with by observation, I don't think if you didn't have LT on this side, I don't think you could include the memory of past environments.
Okay, so we're coming back to using the same link. Sorry, tomorrow from 10 a.m. Don't hesitate to send emails also, or if you have questions and you don't feel like asking in plenary.